Hey, how's it going? Hi, Aaron. It's been back on campus has been it's been a little hectic, not gonna lie. Yeah, there's too many people on campus, so there's no parking. That's the difficult part. Yeah, maybe right now it's okay, but yeah, this morning it was madhouse. Yeah, I ended up having to park on the complete other side of campus, and so looking forward to walking back in the dark through the campus. Yeah, it's a little crazy, but you know, we'll figure something out. Even last semester, I was coming to campus last semester to teach. Even last semester, the parking was getting a little bit, a little bit crazy. But now that everyone's back, it's crazy as hell. Let me a drink of water.
Professor.
Yep.
Do you know where ESE022 is, the lecture room?
ESC, what's the number?
022.
022. That must be one of the side buildings. Because we have the two tall buildings. We're in CS, and the one on the other side is E.
Okay.
And so I think usually those 3-digit numbers are one of the ones on the side.
Okay. It's
Yeah.
probably on the ground floor.
Yeah, ground. Yeah.
Okay.
Hey, Ralph. All right, it's 7 o'clock, so let's go and get started. Good evening, everyone, and good evening from the classroom. So this is our first day back. Although for a lot of you who were at 540, this is kind of familiar territory because we were here all last semester. So, we're back in the same room. But, for those of you who are here for the first time or here on campus for the first time, welcome. So how's everyone doing today? Good. Yeah, it's a late night. Maybe a lot of you guys kind of just got here recently, but it's been a crazy day. Like everyone's back on campus, and I think everyone's kind of forgetting just how everyone forgot how crazy it is, just to find parking and everything. So yeah, I think it'll be an adjustment this week for everyone. Okay. And so the plan for today is we had a little bit of the stiffness notes I want to finish up. So we had one more example that I wanted to do. And then after that, we're going to start our next set of lecture notes on truss equations. Okay? So remember, our first homework is due today. That's the ANSYS activity along with the coding questions. And so definitely that make sure you get those done. I know there's some questions on the coding problems. And so actually, what I want to do first thing today is I do want to go over one problem in particular that I got a lot of questions on. And that's a good one to go over too, because I think it's a good structure. It's a good coding structure to know because a lot of the codes that we're going to do later on kind of follow off that. Maybe not right now, but maybe later on in the future. Okay? I think it's kind of a good one to practice. Right, so I did want to go over that. So hopefully that clears up some confusion on the homework, and then from there we'll launch to the lecture. Okay, and so that's it for my announcements. And so are there any questions besides the coding homeworks I can answer before we get started? Okay, all right, so let me go ahead and switch over to this computer screen. Okay, not this one. Okay. Okay, so here is our activity. Okay, you scroll all the way down, and you come up to the coding prompts. Okay? And so the one I want to go over in particular is part C. Okay. And so part C is the one I usually get the most questions on, and this semester is no exception. Okay. I believe someone asked me about this in the Discord, and so I gave a partial explanation there, but I want to make sure I go over in the lecture for everyone who didn't catch that. Okay. And so what we have here is a matrix, right? And so you can see here it's a 5 by 5 matrix. And the structure that I gave you here is that we have a -2 on all the diagonals, and then we have some ones that are acting as wingmen on certain rows. Okay, and then to construct this matrix, I've given you this kind of pseudocode right here, and so you can see here I've only given you one loop. Okay, and so I think that's the part that's kind of throwing a lot of people off, because normally, or for a lot of the examples we did last week, or I think maybe that was like 2 weeks ago now. Whenever you're assigning entries in a matrix, normally you would expect it to be like a nested for loop like this, right? And so you have 4 i's equal to something, 4 j's equal to something, so that you can visit every single entry. Okay. And so I think what throws people off is that we only have one for loop here, and so the question is how can we visit every single entry in this matrix with only one for loop? Right? And so the way that we do it is kind of first by noticing that a lot of the entries in this matrix are actually 0, right? And so these 3 are 0, these 2 are 0, this one's 0 right here, okay? And so there's actually not that much we need to do in this matrix, because a lot of them are already 0. And we're starting out with a zeros matrix as well, right? And so this first line of code right here, tells us that, we're starting out with a zeros matrix. And so the entries that are already 0, we don't have to do anything about them, and so we can just kind of leave them be. Okay? And so the only other entries we have to worry about then are the non-zero entries. And so the way to kind of view this matrix right here is to kind of view it row by row. Okay. So we look at the first row in the matrix, we look at the second row in the matrix, third row, fourth row, and fifth row. Okay. Right, and actually this loop right here, this for loop I, this is going to visit every single entry in the matrix, or every single row in the matrix. I'm sorry. And so this I is actually going to go between 1 and 5, where I is going to correspond to each row in that matrix. Okay. Okay. And so in this inside this for loop, you can see that we have if statements, right? And in fact, I have most of the first one written for you. Okay. So now that we know that the for loop I is going to be looping over the rows, we can kind of deduce what this if statement here is telling us, right? And so if we could say if I is equal to 1, okay, that means, and if I is going to count over the rows, this means that this condition corresponds to the first row. Okay. And so if we're in the first row of the matrix, that's that's what we're going to do here. And then, you can kind of deduce what the rest of these if statements are going to be. And so we could say here that the else if here, right? Else if means we're going to do something different as well. And so if we look at the first row, right? The first row, we only have one neighbor to the right. That's a 1, okay? Whereas most other rows here have both a left and a right neighbor. That's 1, right? And so the only other one that's different here is the last row, where we only have a left neighbor. And so this else if right here, we can kind of consider this to be, if we're in the last row of the matrix. Okay. And if we're in the last row, we're going to set one entry equal to 1. Okay. And so I'll let you kind of deduce that, based on that. Okay. All right. And then in the else part, remember the else is for every other condition. And so if we're not in the first row and we're not in the last row, we're going to do these 2 lines of code right here. Right? And so this else statement here corresponds to when we're in one of the middle rows. Okay. And when we're in one of the middle rows, we have to assign both a left and a right neighbor for the ones. Right? Okay. And so the last one that kind of throws people off is, what is this last line of code in the for loop as well, right? And so if you notice, this is outside the if statement. And so since this line of code is outside the if statement, this is something that we're going to execute, or this is a line that we're going to execute in every single row of the matrix, okay? Right? I apologize for this mouse. It's pretty jank, right? And so, let's look at our output matrix and let's see what happens in every single row, right? And so in every single row, it's true that we assign a one, and at least a one in every single row, but the locations of the ones are going to be different in every single one, right? What happens in every single row is we assign the diagonal entry equal to -2, right? And so let's go ahead and put that line of code right here. And I've actually written most of it for you. And so knowing that I is looping over all the rows, if we say that B at I comma I, right, this is going to be the diagonal entry. And so if we say that B at I comma I is going to be equal to -2, right, then this is going to assign the diagonal entry of that matrix. Okay, and this happens on every single row, and so that's why it exists outside the if statement. Okay. All right, so that gives a little bit more context on that problem. Just to kind of help you guys out. So I think the key thing with this problem is realizing that the I or the for loop is looping over each of the rows. Yeah.
So that's like my main point of confusion when it comes to these loops. So how did you know that I comma I was going to correspond to the I?
Right. And so from this code snippet, we can see that the I here is the loop variable. And so that's the one that's going to be incrementing, 1, 2, 3, 4, 5. And so yes, exactly. Yeah. And so the I is going to be, it's going to start at 1, and then each time the loop completes, it's going to increment up by 1. And so for the entire first, I call it an iteration of the loop, I is going to equal to 1. And so when you assign, B at 1, 1, that's going to be the first row and the first column of the matrix. And so the next time the loop comes around, then I is going to equal to 2, because it's going to be the second iteration of the loop.
Oh, so it's going to be 2,
2 comma 2, exactly.
okay,
Yeah.
So that will always correspond to that.
Exactly. Yeah. Yeah. And so I like assigning this problem, even though, honestly, this is actually a problem I've taken from another class. And so this class, we're going to go a little bit different direction. But what I really like about this problem is that the fact that we're using just one loop to loop over the matrix, and we're using the loop index to reference different entries in that matrix based on the diagonal. So, when you have kind of a single loop structure like this, you can always locate the diagonal. And so the diagonal entry is always going to be I comma I. And then you can locate different entries relative to that. And so you can go I -1 to the left of the diagonal, I +1 to the right of the diagonal, things like that. Yeah, so that's kind of the main, those are kind of the main kind of tips I want you to get from this problem. Yeah, and of course, we can talk more after class. So I plan on staying a bit after class today if you have kind of more specific questions on the programming. But I did want to make sure I go over that one together, because this one's a pretty important one. Especially once we move forward more with the programming. Yeah. All right. Question in the chat. Will I be able to post a solution? Yes, yeah. So after everyone turns it in and after I grade it, I always post a solution right afterwards. Yeah. Mm-hmm. Yeah. And remember, yeah. So once the solutions are posted, then you can check your answer to that. And I would definitely encourage you to do that, just so that you can kind of see my logic for this. Yeah. All right. Any other questions on this before we return to the notes? Okay. All right, so let me go ahead and stop this. And kind of the mad shuffle that was today, I misplaced my my normal iPad and stylus, and so I'm using Dr. Lee's iPad. And so in the top left you'll see that it's Jinwoo's notebook, and so Jinwoo is Dr. Lee, and so he was nice enough to lend me one after I was like panicking like crazy this afternoon. Okay. All right, and so where we left off was we were talking about the direct stiffness method, right? Where the direct stiffness method is kind of one way that we can implement what's known as the finite element method. Okay, and the finite element process, has a few distinct steps. Okay. Okay. And they're all illustrated by the direct stiffness method. Okay. All right. So the first step in the process is to and this part's usually done for you in the problems, but the first step is always to discretize or mesh your domain. Okay. In other words, you're going to take the domain and break it up into elements. Okay. Most of the time, that's going to be done for you for at least the problems you're going to do by hand. But just know that that's an important part of the process. Okay. Okay. The next step in the process is to form or compute all of the element stiffness matrices. Right? Remember last time we went over the concept of what an element stiffness matrix was, and then we learned how to compute it for a spring. Okay, so every element in a finite element problem is going to have its unique element stiffness matrix. Okay, and so the next step is to go through each and all the elements and compute what that matrix looks like. Okay. Right. The next step in the process is to assemble the global system. Right. And so once you have all the element stiffness matrices, remember by themselves, they're not that useful. And so in order for them to be useful, you have to assemble them into one kind of gigantic system. Right. And so that's what assembly is. Right. The step number 4 is to apply boundary conditions to the global linear system. Right. And so, right after you assemble all of the equations, it's still not in a good position to solve. And so you need to apply boundary conditions in order so that you can, first of all, apply those effects to your system, but also make sure that it also ensures that the linear system is actually solvable. Okay. And step 5 is to solve the linear system, right? And so by the time you're done with step 4, you're going to have a system of linear equations, usually expressed in matrix form. Right? And so once you have those equations, you can solve them. But most of the time, this is usually a very large system. And so this is usually done by the computer. And so in terms of what you are responsible for in terms of the finite element engineer, either you're working out these problems by hand or you're writing the code, most of the time you're going to be just responsible for these 3 middle steps. Okay. And so you're going to be responsible for computing the element stiffness matrices, assembling them into the global system, and applying the boundary conditions. And then once you've done that, what we say is that the finite element problem has been set up. And then once it's been set up, we then pass it off to the computer to solve. Okay. All right, so that's kind of the finite element process in a nutshell. And so, for basically the entire class, we're going to be learning kind of different spin-offs on this process. Mostly, most of the complication is actually going to be in step 2. Okay. And so, a lot of what we're going to learn in this class is different ways to compute the element stiffness matrix. Okay. All right, so that was just kind of a recap of what we did last week. So are there any questions on this? Okay, all right, so let's go ahead and do another example with springs before we jump into trusses. Okay, so let's consider the following system. Okay, and so on one hand, let's say we have a fixed support, Let's say that we have a single spring like this. Okay. Let's assume that this spring is attached to a wooden block. Okay. And this wooden block is going to be attached to two more springs. Okay. Okay. And on this top spring right here, we're going to pull with a force F3. Okay. And on the fourth one, we're going to push with the force F4. Okay. All right. I'm going to go ahead and label all the nodes here. And so the one that's attached to the wall, we'll call that node 1. Okay. We're going to assume that everything attached to the wooden block is going to move together. And so the wooden block is another node. We'll call that node 2. The node up top here, that's going to be node 3. And the node down here is going to be node 4. Okay. All right. And so in addition, we know the spring constants for all the springs. And so this one's going to be Ka. We'll call this one Kb. And call that one Kc. Okay. Okay. And so let me give you values for all these parameters just so we can plug in numbers. Okay. And so Ka, we're going to assume it's 500 newtons per meter. Okay. Kb is going to be 100 newtons per meter. Right. Kc here is going to be 250 newtons per meter. Okay. And then the force values, F3 is going to have a magnitude of 100 newtons, and F4 is going to have a magnitude of 50 newtons. Okay. Right. And so based on this problem, what we're interested in is computing the displacements or computing the deformations of each of the nodes, each of the displayed nodes in the mesh. Okay. So we're going to use direct stiffness to compute displacements of each node in the mesh. Or I should say in this diagram. Okay. All right. And so that's the setup for the problem. And so are there any questions on the setup before we start solving it? Okay. All right. So let's go ahead and run through our process. And so, you know, the domains have already been discretized for us. And so we have 3 elements here. And so we have spring A, spring B, spring C. Okay. The next step is to form the element stiffness matrices. Okay. All right, and so we're going to go element by element. And so let's start with element A. Okay. And so element A, remember when you're forming these element stiffness matrices, you have to take note of what nodes that they're attached to, right? And so element A here is attached to nodes 1 and 2. And so we're going to do F1, F2 is equal to Ka minus Ka minus Ka, Ka times U1, U2, okay? Where we can go ahead and plug in for the values of Ka, okay? So remember Ka here is 500, and so this is equal to 500 minus 500 minus 500, 500, U1, U2 is equal to F1, F2. Okay. And so this is the element stiffness matrix for element A. All right. And so now let's do the same thing, but for element B. Okay, so element B, let's go back to our diagram. Element B is connected to nodes 2 and nodes 3. Okay. Remember, everything on the wooden block counts as 1 because we're assuming that the block is completely rigid. Okay. So element B here is going to be F2, F3, is equal to KB minus KB minus KB, KB, okay. U2, U3. We go ahead and plug in for KB. And so KB in this case is what? 100. And so we have 100 minus 100 minus 100, 100. U2, U3, okay. And then finally, we can do the same thing for element C. Okay, so element C, let's go back to the diagram. So element C is going to be interesting. And so this will be the first time we have an element that it's not connected to continuous nodes, right? And so it's going to be connected to nodes 2 and 4, okay? And so this is going to be F2, F4. This is equal to, and the spring constant for element C is 250. And so we have 250 minus 250 minus 250, 250, okay? U2, U4, okay? All right, and so those are the 3 element stiffness matrices that we have for this problem, okay? So for springs, it's very simple. You just plug in the spring constant into the matrix. You know, the only thing you have to be careful of is you have to make sure you list the right nodes for this. Any questions on this so far? Yeah.
I'm assuming we're just calculating displacement of the x.
Yes, correct. Yeah. And so this is all 1D problems. And so we're just doing displacement in the x. Yeah, good observation. Yeah. Okay. All right. So now that we're done with the element stiffness matrices, let's go ahead and work on assembly. Okay. And so for assembly, you remember we want to combine everything into one global system, right? And so in this case, we have 4 different nodes, and so our global matrix here is going to have 4 rows and 4 columns. So we have F1, F2, F3, F4. I'm going to go ahead and draw in the columns. Even though for 4x4, it might still seem a little bit silly, but it's always a good idea to be organized, more organized than not. Okay. And so here's our global system. And so now we need to slot in each of the element stiffness matrices. Okay. And just like I did before, I'm going to go ahead and color code this. Okay. Let's start with element A. And so element A is connected to nodes 1 and 2. And so we're gonna insert this into the first row, second row, first column, second column. Okay. Okay, so I'm going to draw this nice hot pink box around this part of the global system. Okay. And since we have their values already, we can go ahead and plug those in. Actually, I'll wait. Let me kind of draw the full structure of the matrix first. Okay. Okay. And so next we have element B. And so element B is nodes 2 and 3. And so we're going to go to the second and third row and the second and third column. So that's this area right here. Okay. And so that encompasses all the U2, U3 slots. Okay. Right. And then finally, let's do, I think yellow is good. Okay. So finally, we have element C. Okay. All right. So element C is going to be nodes 2 and 4. And so this one's going to be interesting because it's going to be disjointed. And so it's not going to be, it's not going to be one big continuous box. Instead, we're going to, have them in kind of 4 different places. And so let's because this one's a little bit weird, let's go ahead and use the trick that I talked about last time. And so I'm going to take my pen here. I'm going to go to the second column. I'm going to draw a vertical line down. Okay. I'm going to go to the fourth column and also draw a vertical line down. Okay. I'm going to go to the second row and draw a horizontal line across. And then I'm going to go to the fourth row and draw a horizontal line across. Okay. And so at every location that they intersect, that's where we're going to input an entry into the global system. And so you can see they intersect here, they intersect here, they intersect here, and they intersect here. Okay. And so in those 4 locations, we're going to put an entry or a section of our element stiffness matrix for element C. Okay. So let me go ahead and get rid of these. Okay. Okay. And so first we're going to go to the U2 slot. Okay. Okay. And so I'm going to draw a yellow box on top of that. All right. So it's a little bit hard to see, but we basically have all 3 element stiffness matrices overlapping on U2. Okay. Then we're going to go to the U2 row, U4 column. Then the U4 row and the U2 column. And then the U4 slot, just like that. Okay. All right, so don't be afraid to break up your element stiffness matrices like this. If they don't align perfectly, in one big spot. And once we start getting the 2D problems, this is going to be much more the norm rather than the exception. Okay. All right, any questions on how I chose these spots in the global system? Okay. All right, so the next step is to actually go ahead and fill in the values. Okay. And so for element A, we're going to put Ka in there. And so Ka is 500. Okay, so we're going to do 500 minus 500 minus 500, 500. Okay. Next, we have element B. And so element B is going to be everywhere with the blue. And so Kb is 100. And so we're going to add plus 100 here. Minus 100, minus 100, 100, okay. And then finally, we have the yellow, which is element C. And so element C, we're going to add a 250. So we have plus 250, one too many zeros. Okay. Minus what, 250, minus 250, and 250. Okay. Right. So those are all the spring constant values. And remember, whenever we have something that overlaps, we simply just add those values together. And so on this U2 slot, we have 500 plus 100 plus 250. And so in total, that should be 850. Okay. Right, and there is our assembled matrix. And then everywhere else that that doesn't have that's not under a box, we can just go ahead and fill those entries in with 0. Okay. And so in this case, we don't have that many zeros, but they're there. Okay. All right, any questions on assembly? Yeah.
Can you do the 850 again?
Oh yeah. So the 850 was just a sum of all 3 components. So you can see here that element A is in this intersecting on this box right here. Element B is there as well, and then element C. And so the 850 was just a sum of 500, which was contributed from element A, plus 100, which is contributed from element B, plus 250, which is from element C. I did it, yeah, okay. Yeah, 850. Mm-hmm. Okay. And so now that we're done with assembly, the next thing we're going to apply is boundary conditions. And so let me go ahead and write the matrix out again, just so that we can have something to modify. Okay. So all I did was I just rewrote our assembled matrix. Okay. Okay. And so remember the reason we apply boundary conditions is because otherwise we wouldn't be able to solve this system. And so because this is a perfectly symmetric system, it doesn't have a determinant, or its determinant is 0. And so we need to apply boundary conditions on this guy. And so let's go back to our diagram to see what our boundary conditions are, or what our modes of constraints are. Right, and so the first thing we notice is that since node 1 is attached to the wall right here, it is at a fixed support. Okay. And when a node is fixed like that, that means its displacement is 0. Okay. Right, and so a fixed support basically means that U1 is equal to 0. Okay? And this is a Dirichlet boundary condition because we're directly specifying the solution variables. Okay. Okay. And then on nodes 3 and 4, we can see that we're applying a force boundary condition on here. Okay. And so we can say that little f3 is going to be equal to big F3. Okay. And little f4 is equal to big F4. Okay. Where both of these are, since they're forces, these are Neumann type boundary conditions. Okay. Or in other words, they're modes. And one more boundary condition, not really a boundary condition, but we need it to complete the system. Since we don't have any forces acting on node 2, we can say that F2 is equal to 0. Okay. Okay, so now that we have all these boundary conditions, let's go ahead and apply them to our system.
So what is the little just saying that part of the matrix corresponds to our force on the
Exactly, yeah. Yeah, so when I say little f, that's what I'm referring to is this this vector on the left here. Yeah. Okay. All right, so let's go ahead and apply these. So let's start with the Dirichlet boundary condition, or let's start with the fixed constraint. Okay. So remember our fixed constraint basically told us that U1 is equal to 0, right? And so what we're going to do, remember, whenever we have a Dirichlet type boundary condition, we're going to replace that entire row of the matrix. Okay. And so we're going to take this entire row and then turn it into U1 is equal to 0. Okay. So let me go ahead and erase this, all of these guys. Okay. Right. And so if U1 is equal to 0, that means we need a 1 on the diagonal. Okay. 0 is everywhere else. And then a 0 on the left-hand side. Okay. And so the replacement of that row basically says that, remember, if we applied the vector-vector multiplication of this row and this column, okay, then we get U1 plus 0 times U2 plus 0 times U3 plus 0 times U4, and that's equal to 0. Okay. And so this equation, by performing that replacement, has made its way into our matrix. Okay. Okay. All right, so the rest of the boundary conditions here are Neumann type boundary conditions. And so there's not much to do here except for replace those values. Okay. The only thing you have to be careful here is the directions of the forces. Okay. All right, so let's start with F2. And so F2, we're not applying any loads on F2 or node 2. And so the F2 there is just going to be equal to 0. Okay. Next, we have F3. And so since we're directly applying the force of big F3 on this on that node, we're going to have an F3 right there. And in fact, F3 was what? 100. Okay, so let me go ahead and put that in. Okay. And then we come to F4. Okay, so remember, F4 has a magnitude of 50 newtons, but the direction that it's going to is on the left, right? So if we go back to our diagram, you can see that F4 here is pointed to the left, right? And so that's in the negative x direction. And so we need to make sure that we incorporate that or communicate that into our equations. Okay. And so since F4 is pointing to the left, we put that in as a minus 50. Okay. Right. And so now that we, now that we've defined our matrices here and we define our vectors, now we're ready to solve. Okay. And so before I show you the answer, are there any questions on how we set this up? Okay. Okay. And so now that we have our linear system, we can just go ahead and solve. Right. And so the way that we're going to solve most of the time in this class is through MATLAB. Right. And so remember, to solve a linear system in MATLAB, you have to define a variable that defines the left-hand side matrix. Okay. And so let's say that we define a variable called LHS matrix, and it's this 4 by 4 we have on the left. And then you define a vector called RHS vector. And so that's going to represent all the forcings and boundary conditions on there. Okay. Right. And then to get the solution, we just need one line of code. And so the one line of code is RHS matrix, or RHS vector, excuse me, backslash LHS matrix. Semicolon. And so this is going to perform all the hard work for us. And so if we do that, then we get our solution. Okay, so I'm going to go ahead and give it to you because, so you don't have to pull out MATLAB. And so you have U1 is equal to 0, U2 is equal to 0.1 meters, U3 is equal to 1.1 meters, and U4 here is going to be minus 0.1 meters. Okay. So a little bit crazy. And so, under these forces, and the springs I chose are really weak just to make sure the numbers are reasonable. And so you can see here that we get 1.1 meters of deflection, which is actually quite a lot. Okay. But the exact answer is not that important for this example. So I just wanted to show you kind of another way or another trial where we go through that entire process of element stiffness matrix, assembly, boundary conditions, and solve. Okay. All right. Any final questions on this example before we move on to trusses? All right, question. So what's the difference between that and LinSolve? So yeah, LinSolve does the exact same thing. So they both do the same thing. I prefer backslash just because it's less typing, but LinSolve will get the job done as well. Yeah. Okay. All right. And so that's the introduction to the stiffness method, right? And so maybe you've never thought of springs that way, but springs are a good way to kind of illustrate this whole kind of finite element process. And throughout this whole semester, we're just going to be adding kind of more nuance to it, different kinds of elements and different ways to construct the element stiffness matrices. Okay? And so the first kind of step in this is to kind of increase our arsenal of element types. Right? And so the next type of element that we're going to look at are known as truss elements. Okay. All right. And so truss elements are, they're actually a very close cousin of the spring. Okay. And what they represent are basically slender structural elements that can only support tension and compression. Okay. Okay. Sometimes they're called bar elements. But most of the time I call them trusses. Okay. And so visually they look like this. And so they kind of look like a slender rod. Okay. and they can only support tension or compression along its long axis. Okay. And so there's gonna be no shearing, no bending, or anything like that. And so that'll come later when we do when we do beams and frames. Okay. All right. So what are the important properties of a truss element? And so first of all, we have the length, and so that's going to be important. Okay. Next, we have its cross-sectional area. And in addition, we have a property of the material itself, which is the Young's modulus. Okay. And we often give that the symbol E. Okay. And so we have E and A and L. And I circled those in the wrong order, but you get the idea. Okay. All right. And so the constitutive equation that governs a truss it's actually also called Hooke's law. And so the guy Hooke was kind of busy, but this is kind of a more general Hooke's law. And so another way that people have described this is as a linear elastic relationship. Okay. So we'll call this linear elastic Hooke's law. Governs truss behavior. Okay. And so mathematically it looks like this. And so we have a relationship between the stress inside the truss element. This is equal to the Young's modulus of the material multiplied by the strain. Okay. So here we have stress. Here we have strain. And here we have Young's modulus. Okay. All right. And so we're going to work on this equation right here in order to, get a, in order to help us obtain the element stiffness matrix. Okay. All right. Any questions on this so far? Okay. All right. And so let's work on this equation here so that we can obtain the basically, we're basically going to run through the same process we did with the spring. And so we're going to use in this case Hooke's law again, and then we're going to use that to get our 2x2 system of our of our element stiffness. Okay. And so the system that we want to go with is a truss element in static equilibrium. Okay. Okay. And so if it's in static equilibrium, just like the spring, we have equal and opposite forces on both sides. Okay. And so in this case, we're going to assume that they're tensile forces. And so we have a rightward force on the right node and a leftward force on the left node. And they're equal in magnitudes, that we are, we are in static equilibrium. Okay. And so and so just like I did with the with the spring, I'll label the left node node 1 and the right node node 2. Okay. And just like I did with the spring, let's define a displacement of the left node as U1 and the displacement of the right node as U2. Okay. All right. So now let's start substituting terms into our Hooke's law. Right? And so the first thing I want to start with is stress. Okay. And so remember the units for stress, stress represents kind of the structural stresses within the material that kind of helps keep it in static equilibrium. Right? And so for a simple case like this, where we assume that the only forces that are acting are purely tensile and compressive, one way that we can express this is as a ratio of the tensile force divided by the area. Okay. And so stress, or excuse me, so the stress is going to be the force divided by the area. Okay, and so we have stress, and so we know the force in this case, and so since we're assuming a static equilibrium case, and so our force is going to be the tensile force T divided by the area, okay? Right. And so we can go ahead and substitute back into our equation, okay? And so we substitute this back that we get. So we substitute that back into sigma is equal to E times epsilon. Okay, so we substitute that in. We have T divided by A is equal to E times epsilon. Okay. And if we move A to the other side of the equation, so we multiply both sides by A, and we get T is equal to AE epsilon. Okay. All right. So that's good, right? And so you know, the reason I did this is so that we can express this in terms of the properties of the truss itself, right? Because right now what we have in Hooke's law is these are really useful quantities, but they're not in terms of the properties that we know. Okay, and so the properties that we know are the Young's modulus, the length, and the area. Okay, and so by making that substitution for sigma, we work the area back into the equation. Okay. All right. So the next thing that we need to substitute for is the epsilon here. Okay. And remember, strain, the way it's defined. Strain is defined as the relative change in length of the truss element. Okay. Okay. And so we have epsilon. Okay. And so the relative change in length, and so if we say the change in length is delta L, and if we divide that by the original length L, that's going to be our change in length. Okay. Right. We can plug in for the change in length, and so remember, because we have the nodal displacements, right? And so the change in length right here can be expressed in terms of the difference of our nodal displacement. Okay. Right. And so the change in length here would be simply U2 minus U1. Okay. All divided by L. Okay. All right. So let's go ahead and plug this back into this equation here. Okay. Okay. And so now if we plug that into our Hooke's law, what we get is T is equal to AE divided by L, okay, times U2 minus U1. Okay. Okay. Right, and so we've successfully transformed our Hooke's law equation in order to incorporate all the properties of the truss bar that we know. And so we have the area in there, we have the length, we have the Young's modulus, and then T and U's are the force and displacement. Okay, but we're in pretty good shape. And so all we have to do is just a couple more substitutions, and we'll have our element stiffness matrix of our of our truss. Okay. Any questions on what we've done so far?
You want to meet your displacement, correct?
Correct. Yes.
Do we have them drawn up there in the diagram where it says static equilibrium?
Yeah.
They're both the nodes are moving the same direction.
Yep. So I drew them both as positive here just to show which is this positive convention. But in reality, in order for it to be static equilibrium, U1 has to move to the left. And so that's why we have a minus U1 right here. Yeah. Yeah, I draw them both positive just for the sign convention, but yeah, you're right. U1 has to move to the left. Okay. All right. And so now that we have this equation right here, let's apply this at each of the nodes. Okay. Okay. All right, and so if we do that, we're going to get two equations for our system. Okay. All right, so let's do node 1, right? And so node 1, in order for our static equilibrium case, we can see that we are applying a force in the negative direction, right? And so at node 1, okay, we're applying a force F1, and that F1 is equal to minus T, right? Just because that force is going to the left. And so if we plug in for minus T here, what we get is minus AE divided by L times U2 minus U1, okay? And so if we kind of simplify that, we get F1 is equal to AE over L. I'm going to distribute that negative through the equation right here. AE over L multiplied by U1 minus U2. Okay. All right. And so that's the first equation that's going to be part of our element stiffness matrix. And so the other equation is going to be found when we apply this at node 2. Okay. Okay. And so at node 2, we have F2 is equal to T. And so we have AE over L times U2 minus U1. Okay. And so if we kind of clean this up, we get F2 is equal to AE over L multiplied by U2 minus U1. Okay. Right. So those are our two equations for our two nodes. Okay. And so now let's put this in matrix form. Okay. And so we put in matrix form. We're going to have F1, F2. Okay. This is equal to AE over L minus AE over L minus AE over L, AE over L. Okay. Multiplied by U1, U2. So I basically applied this equation down here. And so the negative I applied through it. So I swapped the sign of U1 and U2. And so for the first equation, the first entry should be positive, and the second entry, which is U2, should be negative. And then the opposite is true for the F2 equation. Yeah. All right. So, but since writing out AE over L 4 times is a pain, usually what we do is we factor it out, and so we say that this is equal to AE over L, okay, times 1 minus 1, 1, U1, U2. Okay. And so this, what we have here, this is the element stiffness matrix. Or I guess I should say element stiffness system for a truss element. Okay. All right, and so now that we have the element stiffness matrix for a truss, we can start using it to do problems. Okay. Any questions on this before we do an example? Yeah.
The F1 was negative T, but we just.
So the negative I distributed through, and so the negative here comes right here, and so normally T is equal to U2 minus U1. but I distribute this negative through to this part of the equation. So I swapped U1, U2. And so you end up with a positive U1 and minus U2. And so that's where the negative comes in for F1. Yep. Mhm. Right, question? Let's see. Okay. Any other questions on this? Okay. Actually, before we do an example, I want you to notice something. And so, this should look very similar to our spring element stiffness, right? So if I can use the margin. Right, so our spring element stiffness matrix looks like that, where we have our spring constant, minus spring constant, minus spring constant, spring constant, right? This looks very similar. And so, we can see here we have a positive, a negative, positive, and they all have the same, numerical value, or numerical magnitude, okay? And so, the truss and the spring are actually very close cousins to each other. And so, the way some people like to think of it is that this combination of terms right here, this AE over L, some people call this like the effective spring constant. The effective spring constant of the truss bar, okay? Because it plays the same role. And so and in fact, they have the exact same units too. And so if you do AE times divided by L, you'll see it has the same units of force divided by length. And so some people think of this as like the effective spring constant. And so if that kind of helps you kind of do these problems, then, then that's one way to think about it. Okay, and so I think we have just enough time to do one more example kind of really quickly, okay? And so, we have the following assembly of three bars. Okay, and so we have a fixed wall on this side. Okay. We have one element like this, another element like this, okay. Another element like that. Okay, and so we'll call this lowercase a, lowercase b, lowercase c, okay? It's hard to use capital letters here because big A also means area. And so I'll label the elements by little letters, okay? So we have three bars, okay? Let me label the nodes. And so we have node 1 that's fixed to the wall there, another node there, another node there, another node there, okay? All right, so let's list some properties. And so the Young's modulus for element A is equal to 30 times 10 to the 6th psi. Okay. The Young's modulus for element B is also 30 times 10 to the 6th psi. The Young's modulus for element C is 15 times 10 to the 6th psi. Okay. Right. They all have the same area. And so the area for all of them is going to be, or excuse me, no, they don't have all the same area. And so the area for elements A and B are going to be 1 inch square. Okay. While the area for element C, this is going to be 4 inch square. Okay. But they do all have the same length. And so the length for all of them will be 30 inches. Okay. And so the total length from here to here is going to be 90 inches. Okay. Okay. All right. And so just like we did with our first example today, we're going to use the direct stiffness method, this time with trusses, to compute the displacements of all the nodes in this assembly. Okay. All right, and so we're going to follow the exact same process we did before, except now instead of springs, we have truss elements. Okay? But again, that's only going to modify how we compute the element stiffness matrices. Okay, any questions on the problem setup here? Okay, so let's go ahead and start doing it. And so the first step, first step is discretize the domain, but that's kind of already done for us. Okay. And so next, let's compute the element stiffness matrices. Okay. And so we have 3 here. Okay. And so let's start with the element stiffness matrix for element A. Okay. Just to make our life a little bit easier, let's compute AE divided by L for element A. Okay. And so the value of the area times the Young's modulus divided by length for element A here is going to be 10 to the 6th pounds per inch. Okay. Right. And so we take 1 multiplied by 30 times 10 to the 6th, and we divide by 30. We end up with 10 to the 6th. Okay. And so for element A, what we have is F1, F2. Okay. Since element A here is connected to nodes 1 and 2, that's why we put F1, F2 there. Okay. This is going to be equal to 10 to the 6th minus 10 to the 6th minus 10 to the 6th, 10 to the 6th. Okay. And this is multiplied by U1, U2. Okay. Okay. All right. And so for element B has the exact same material and geometric properties. And so if we take the AE over L for element B, we end up with 10 to the 6th as well. Okay. And so it's really tempting to say that element stiffness matrix of A is equal to element stiffness of B. Okay. It's really tempting to do that, but remember the other important piece of information you need here is you need to know which nodes the elements are attached to. Okay. And so, when you're kind of first starting out, when you're kind of first doing these problems, these problems kind of take quite a few steps to do. And so I would encourage you to actually write out, the full element stiffness matrix for each element, just to make sure it's all accounted for. For these ones, I know it seems kind of trivial because, there's only a few, but once we start doing 2D problems, once we start doing beam problems and frame problems, the place where I see people mess up the most is not really in the math, but just in staying organized. And so, it really helps to kind of, even though I know it's a pain to write out, repeated information, staying organized is really helpful for these kinds of problems. Okay. And so with that said, for element B, we have F2, F3, because element B is connected to nodes 2 and 3. So we have 10 to the 6, minus 10 to the 6, 10 to the minus 10 to the 6, and a positive 10 to the 6. Okay. U2, U3. Okay. And finally, we have element C. Okay. And so the AE over L of element C, and so we have the area is 4, and then we're multiplying that by the Young's modulus, which is 15 times 10 to the 6 psi. We divide that by 30, and we get 2 times 10 to the 6th pound per inch. Okay. And so we convert that to an element system. We have F3, F4, because element C is connected to nodes 3 and 4. Okay. I'm going to be lazy this time, and so I'm going to put 2 times 10 to the 6 out in front. So you have 1 minus 1 minus 1, 1, and then U3, U4. Okay. And so those are all the element stiffness system, or all the element stiffness matrices for this problem. Okay. All right. Any questions on this? Okay. All right, so that's part A. So part A of the problem is find the element stiffness matrices. Okay. Part B is assembly. Okay. This one's a little more straightforward because we have things in nice slots. Okay. Okay, so for assembly, okay. we're going to have our 4x4 system. Okay. Actually, let me do this. It's going to save us a little bit of writing. Since we know there's going to be a 10 to the 6 out here, so I'm going to put that 10 to the 6 there. Okay. And so we have all our rows labeled just like that. All right, so first we have element A, and so element A we know is acting on nodes 1 and 2. Okay, so we're going to put a box around here. Okay. Next we have element B. Okay. Element B is nodes 2 and 3. Okay. Okay. And then finally we have element C. So element C is nodes 3 and 4. Okay. Just like that. Okay. All right, so let's go ahead and add in the values of our element stiffness matrices into the appropriate slots. And so for element A, you can see here we have 10 to the 6, minus 10 to the 6, minus 10 to the 6, 10 to the 6, okay? And so since I've already put a 10 to the 6 out in front, I'm just going to put a 1, minus 1, minus 1, and 1, okay? Next, we have element B. And so element B is going to be a 1 in the top left, a minus 1, minus 1, and a 1 down here, okay? And then for element C, it's going to be 2s, okay? Because remember, our element C is 2 times 10 to the 6, so we have a, not right there. So we have a plus 2 here, minus 2, and 2, okay? Okay. And so if we combine these, you can see here we have a 2 here and a 3 here, okay? So we have a 2 and a 3, okay? And we have zeros everywhere else. Okay, so we have 0, 0, 0, 0, 0, 0. Okay. And so that's our assembly. Okay. All right. Any questions on how we assembled this this system? Okay. All right. So one thing I forgot to mention when we were making this problem is we need a forcing. And so right now we don't have any loads. And so the forcing on this problem is actually acting on node 2. So if I can go back up to here, I'll scroll down again in a second. Okay. And so for this problem, our forcing, actually, let me try this out. This freaking rainbow. That's trippy. Okay. All right. And so for this one, we have a forcing of 300 pounds, 3,000 pounds, excuse me. That's trippy. I don't like that. Okay. Okay. And so this tells us that, because our forcing is being applied on node 2, then F2 is going to be 3,000 pounds. Okay. So that's one of the loads we're going to have in our system. Okay. We have no loads applied on node 3. And so for node 3, we're going to have F3 is equal to 0. Okay. In this problem, we actually have 2 fixed supports. So we have a fixed support on node 1 and a fixed support on node 4. Okay. And so we need to make sure that we apply both of those fixed supports onto the problem. Okay. Okay, so let's go ahead and apply boundary conditions. And so that's part C of this problem. Okay. So let me go ahead and rewrite our system here. Okay. Okay, so we have F1, F2, F3, F4. Okay. I'm not going to put the 10 to the 6 here because it's going to interfere with the boundary conditions. Okay. Okay. All right, and so let's go ahead and apply these boundary conditions. So let's start with the fixed supports. Okay. And so we have a fixed support on nodes 1 and 4, right? And so that means we're going to change our entire first row to 1, 0, 0, 0. Okay. And our last row is going to be 0, 0, 0, 1. Okay. And so those are going to be the fixed supports on nodes 1 and 2, or 1 and 4, excuse me. Okay. Then for everything else, we're going to keep the same values. And so we have a minus 10 to the 6th. We have a 2 times 10 to the 6th, minus 10 to the 6th, 0, 0, minus 10 to the 6th, 3 times 10 to the 6th, and minus 2 times 10 to the 6th. Okay. Right. And so for the middle rows, I just brought down the values from our assembly, right? Because we don't replace those rows. And actually, we're supposed to replace these as well. Okay. Right. And so the right hand, and so the forcing vectors are going to be 0, 0 there. Okay. And then all that's left is to apply our forcing values here. Okay. And so since on node 2, we're applying a rightward force with a magnitude of 3,000 pounds, so we put 3,000 there. Okay. And then for F3, since we're not applying any forcing and we don't have any Dirichlet boundary condition on that one, we put a 0 there. Okay. Right, and so with that done, and so with that done, there is our system. Okay, and so again, this is as far as I would ask you to take it on an exam or anything. Okay, but if you do have MATLAB available to you, for the homeworks, we can go ahead and plug this into MATLAB. Okay, just so that you have some finality in this. Okay. Okay. And so if you solve this system in MATLAB, you get the following results. And so you have U1 is equal to 0 inches. Okay. U2 is equal to 0.0018 inches. Okay. U3 is equal to 0.0006 inches. Okay. And U4, because it's a fixed support, is 0 inches. Right, and so if you actually solve the system in MATLAB, this is what you would get. Okay. All right. So any final questions before we wrap it up for today? Okay. All right. And so that's all we got time for today. And so thank you guys for coming today. So our first I'll say semi-in-person lecture, because it seems like there's half people here, half people at home. So thank you guys for tuning in. And so on Wednesday, we'll pick this up again. And so there's one more small part to this example I want to show you. And then we'll start talking about truss problems in 2D. Right. So have a great evening, everyone. If you have any questions on the homework, I'll stick around for a bit to answer as many as I can. And if not, I'll see you on Wednesday. Thanks, Aaron. See you Wednesday.
I think I'm kind of understanding that second problem now that I talked to you about.
Okay.
You talked about it. So I ended up figuring out the rest of them, but honestly, it was just kind of by I just looked at your code and I was like, all right, I think this is what it's gonna be. And then I was just like, okay, let me see what happens if I plug in these numbers. And I mean, I got it right on my first try both times. I was actually kind of surprised. Like, I still don't fully understand. Like, okay, this is what the loop is doing. So maybe this will help, right?
Yeah.
Okay, so I get this. This is the count.
Yep.
And with just this one for loop, you're going like this: 1, 2, 3, 4, 5.
Yep.
1, 2, 3, 4, 5, like that, right? 1, 3, 4, 5. Like this, right?
So you're only doing it once, and so since there's only one for loop, it's just one count from 1 to 5, and so you're only repeating this loop just 5 times. and that's it. But each one is we're gonna reference each of the rows in the matrix.
Yeah, like you're doing it 5 times, right? Like 1, 2, 3, 4, 5, 1, 1, 2, 3, 4, 5, 2. Is that what you're saying?
No, so it's so each one, and so we have just one for loop. Okay, I'll do it on here. Okay. And so on each for loop, right? So we have 4 I is equal to 1 to 5, right? And so the way I think about it is that this loop is gonna iterate 5 times. And so one kind of journey from the top of the for loop to the bottom, that's one iteration. And so it's gonna go 1 down right here, and then it's gonna reset up like this.
Oh, so it's gonna go 5 times.
Exactly. And so it's this whatever code is in the middle here is literally going to repeat 5 times. And each time, the I is going to have a different value. So the first time down, I is going to have a value of 1.
1, and then 2, and then 3.
Exactly. Right. And so for this matrix looks like this. Oh, no. All right, so it's going to be minus
Minus
2,
2.
1. Yeah. I think I'm missing a row. There we go. Okay. And so the key kind of logical leap here is to say that each of the iterations of the loop, they correspond to each row in the matrix. Right. So that's kind of the logical leap, because when you loop a code 5 times, you can do kind of anything that you want. But for this time, for this logic, where I'm saying that each iteration of the loop, we're going to set each row of the matrix kind of separately. And so think of kind of building this matrix from scratch. And so that's kind of where we want to go. But where we start is something like this. Right?
Yeah, with all zeros.
Exactly. And so we're kind of build this matrix kind of row by row. All right, so let's do I is equal to 1 first. And so I is equal to 1, we know is the first row in the matrix. And so when we start to build this first row,
Yeah,
the first
we're
thing.
saying- okay, so this is the first row.
Right.
So we're saying that if I is equal to 1, and then so we have B 1, comma, I plus 1, right? Because we want to reference that.
Exactly. Right.
So 1, but how does like wouldn't 1, 2 be? Oh yeah, that's right here. Okay, so row 1, column 2. Okay,
Exactly.
perfect. Okay, yeah. So we want to reference that. So we're saying that if I is equal to 1, then that is equal to 1.
Exactly.
And then we're gonna check the last row now.
Right. So the thing with if statements is that once one of these things get triggered, then it ignores everything else. And so it's
Okay.
literally just it's like a choose your own adventure. And so
Yeah.
you choose one.
I'm better with the if statements
I see. That's good.
than I
That's
am
good.
with the for loop. So this makes more sense because you just say, if it's this, then just do that.
Exactly.
It's way easier to understand.
Right. Right.
The for loop thing is, I've always had trouble with that for years.
Mhm.
So, okay, so now we have this, right?
Yep.
Else if, so now we're considering the last row and we want to hit this.
So we haven't hit there yet. So the if I is equal to 1, remember I is the loop variable.
Okay.
And so we've only chosen one path here because our I is still 1. Remember, we're still coming back 4 more times later. And so since we chose this one and we did B I comma I plus 1, then we've done that, and we ignore everything else in the if statement. But we're going to come back to it later. And so for now we're just going to leave it, and then we're going to go to the end of the for loop, which is this one right here. B at I comma I is equal to -2. And so now we assign this one right here, which is 1 comma 1 is equal to -2.
Okay, but I thought that was a tangent.
So that's outside the if statement.
Yeah.
But it's at the end of the for loop, but it's still inside the for loop. And so the for loop, it's everything between for and end. That's the code that we're going to repeat 5 times.
Okay.
And so, since we kind of reached that end right there. Oh, so it's after the end of the if statement. So there's 2 ends right here. And so there's the end for the if statement.
Yeah.
And there's the end for the loop. And so you kind of have to look at the indenting to see, this end right here corresponds to this one. But this B, I comma I, that's
part of
still,
the
in
for loop,
it's
yeah.
still part of the for loop, and so that's
Okay.
why we still repeat it.
Okay.
Okay, so that's the first time down. And so after the first time down, now I is equal to, or I is going to be 2, because this is our second iteration.
Yeah.
And so now we're going to be building this row in the matrix, right?
Wait, so how come you said that the else if was second?
So the else if is, so that's just kind of the ordering of the if statement. So whenever you,
Okay, I'm thinking about how to write the MATLAB code. Okay, and you're walking me through it in terms of like the amount of steps that we're.
exactly,
Okay,
yes,
okay,
yeah.
okay.
So when you write the MATLAB code, the else if has to be the second one. Because when you do else, there's nothing else can come after that.
And it just makes sense to do it this way because of the way that this matrix. is
Exactly,
structured. Okay.
exactly, yeah.
Okay, so now we have 2, and we know that we need to hit this and this.
Exactly,
Because we're
yeah.
already structured.
Right.
So I'm assuming it's gonna be I plus 1 comma I minus 1.
So it's still going to be, we're still going to have the row index is still going to be I. Because remember, when you reference a matrix, it's row,
Oh, row
comma,
column.
comma. And so for this case, since we're building it row by row, the first one is always going to be I right here. And so we have B, I, comma, I plus 1. So this is in the else, right? Because we're in rows 2, 3, or 4.
Okay, yeah.
Right.
Oh, okay. I was thinking you could just put them both into one, but we still need to reference. Okay, but we can't do that because if we put I minus 1 here, then it would kick us back up. So it would
Exactly.
kick us back up.
Exactly.
Okay, so we need that to register the fact that we're in. Okay, but we need 2, 3, and 4. So how come you didn't have 2 of them?
So
Or
this
3
is,
of them. How come you didn't have 3 of them?
so remember, we're still in the for loop, and so we're still going to repeat this 3 more times. And so we're just doing one row at a time right here. And so this is the second row right here. And so since I is equal to 2, right? So you can just plug in I is equal to 2.
I see.
So 2,
Okay,
3,
I
and
see.
then 2, 1.
All right.
And so that's going to be
So it's gonna hit both of these in row 2.
exactly,
And then when we come around for the third time, it's gonna hit both of these in row 3.
exactly, right,
And then when we come around for the fourth time, then it's gonna hit those. And then it's gonna
Exactly.
hit the last one. Okay.
exactly, right. So
Okay.
that's why I put everything in terms of I,
Okay.
so that when you go around the loop, these automatically update to what they need to be for that row.
That makes sense.
And so after the if statement there, we're gonna have a 1 here, a 1 here, because we have, these guys in the else. And then we still hit this one, right? Because this is still in the for loop.
Mhm.
But now I is equal to 2. And so we have B 2 comma 2 is equal to minus 2.
Okay.
Right. And so that's how that one becomes that.
Okay.
And so now the I is equal to 2 is done. And so now we come back up to the top of the for loop. And now I is equal to 3.
Hmm.
So now we're gonna start the third iteration.
And now we're gonna fill in that third row.
Exactly. And so we're still in the else condition. So the else is still rows 2, 3, 4.
Mhm.
And so we're gonna actually use this exact code right here. But now I is equal to 3. And so we have 3, which is I, and then I plus 1 is 4.
Yeah.
And so 3 comma 4 is this one right here, right?
Mhm. Mhm.
And then we have 3 comma 2. And so that's this one right here.
Yeah, and then it doesn't matter what order you write these in, right?
Right, exactly.
Okay,
Yeah. And then once again, we visit that we go to this line
And
because
then
that's outside
check
the
our
if.
negative too.
Okay. And then now that the third iteration is done, now we come back up to the top of the loop again. And so now this I is going to equal to 4, right?
Mhm.
So now we're doing row 4 right here.
Mhm.
And so we're still in the else, right? And so the else, we're going to do these 2 lines of code right here again.
Again.
But then it's I is equal to 4, so we have 4 comma 5. And so that's this guy right here. And then we have 4 comma 3, which is that one right here.
Which is the other side.
Exactly. And then we do bi comma I, which is 4 comma 4. And that's that one.
Mhm.
Okay, and then now we're in the final loop. And so now we kind of come back up to the final time.
And we're at 5.
Exactly. And so now you finally get the else if right here. So it is a little bit disorienting because you do this one first and then you do these 3.
But it's just because of MATLAB.
It's just because of the way it's factored. And so this else if here,
So we're gonna have BI. And then we need to hit.
Well, first
we
let's-
need to hit 5 comma 4, right?
exactly. Yeah, but first let's talk about what's in the else if, right?
Oh,
Because for the if, the way we check if we're in the first row is if I is equal to 1,
Mhm.
right? And so the last row is going to correspond to
I equal 5.
exactly.
And then so we need to hit 5. So we need to hit 5 4. So we're gonna say I minus 1.
Exactly. And so that's going to hit this guy. And so since this guy is we chose this path here, we ignore the else, we ignore this if, and we finally end up with this guy right here. And so we have -2. Just like that.
Cool.
Yep.
All right.
Yep. So that's the logic for that one. It takes a while. And so, it's one thing I think to kind of go through it the first time, but I think kind of the more that you kind of talk it through and kind of be exposed to it, then, you kind of get more used to it. And we'll be doing a lot more of this as well.
Okay.
And so the next big MATLAB thing is actually not for a few weeks actually. So we're gonna write a MATLAB code to solve basically problems like this. So like the one that we did in class today.
Okay.
And so we're gonna set up a MATLAB code to kind of solve a generic example of this.
Okay.
So that's kind of a pretty big leap, but we'll go through it kind of slowly in class, and because I want everyone to kind of get caught up with that one.
Okay. Sounds
Yeah.
good. Yeah. And then honestly, I'm pretty tired right now. I just want to get this done and turn it in, but I'll come to office hours this week, and so we can like talk through the other ones. and
Sure.
Just so I can get a little bit more practice.
For
on,
sure,
like
for
the
sure.
logic for
Yeah.
that, because I still have trouble with this.
So my next
But,
one,
this like definitely makes sense, right? But what
Mhm.
I'm afraid is like, okay, do this, and then I'm just you know what I mean?
It,
Like,
it,
oh my
it, take,
God.
it takes a lot of practice. Yeah, it takes a lot of a lot of just being exposed to it, and then you kind of just start getting used to it over time.
Yeah, definitely, definitely.
So I have
This is
office hours.
just- Yeah.
I have office hours tomorrow at 9, and so
Mhm.
if you can't make it, you can come on Zoom.
Okay. Yeah,
Um,
I'll probably do that.
And then the next one is Thursday at 1. Those are my office hours.
Thursday at 1, I can for sure make that.
Okay,
Oh, is
great.
it not Wednesday anymore?
No, because
okay.
my Mondays and Wednesdays are crazy because I
booked.
take 3 classes. So
Okay.
and so I have one on Mondays just to keep it flexible, but Wednesdays I want to keep it free.
Okay. Thursdays for sure. Thursday for sure I can come. Tuesday, I will also try to. Maybe Thursday will just be better, just because I go to the gym in the morning on Tuesdays.
Mhm.
And I don't know if I'm gonna finish by that. Or maybe I can just go to the gym early. I don't know. Either way, I'll see you on Tuesday
Okay.
or Thursday.
Okay, sounds
All
good.
right. Thanks, Dr. Jack.
Yep, no problem. Sorry, Marilyn, I just saw your question in the chat. Yeah, I can go over 5D one more time. Let me pull it up actually. So it's easier for me to see.
You're gonna do 5D?
Yes.
Okay, let me know.
Okay. All right, so 5D. All right, this will be a little weird because I think people on Zoom will see my iPad, but people here will see I just need to write it down. Okay, so 5D, we have a matrix C. Okay. 4, 5. That's 5 by 5, right? Okay. I'm like running on fumes. I haven't eaten anything since noon. But I'm gonna try my best.
Professor, I have one quick question about
Yeah.
this. Is
Uh-huh.
this for looks or is this required?
For the double.
Is that for looks or or is it required?
It's required. And so so when you have a compound if statement, the 2 vertical lines mean 4.
Okay.
And so we're checking basically 4 conditions here. And then so this says that if any of these conditions are satisfied, then we pop it.
Okay.
Yeah. Mhm. Okay. So let me go ahead and write the structure here, and then because there's some people in the class I want to look at it too. Yeah.
Quick question. Can you just check out my screen for a second?
Okay. Let me answer this one first, and then I'll come over. So then we have if and okay. Oh, where did Zoom go? Did Zoom close? Oh no, Zoom's right here. Okay. Okay, and so here is this is 5D. Okay, and so you can see here we have kind of I call this like a ring of ones. Okay, and so you can see here that we have ones on the outside and all the zeros on the inside. Okay, and so first thing to note here is that most of the time when we're building up matrices, we're going to start with the zeros matrix, right? And so I believe we have C is equal to 0 is 5, 5. Right, and so we're going to start with all the entries in the matrix being 0. And so that means the only entries that we have to worry about specifying or assigning are just the non-zero entries. And so in this case, all the non-zero entries are all the ones, okay? And I did not, okay, well, okay, whatever. Okay, and so I guess I had already kind of filled in some of the code for you. And so, here, this is a nested for loop example. And so you can see here we have 2 for loops. And so we have one for loop that goes from 1 to 5, and another for loop that also goes from 1 to 5, okay? And usually when you have a nested for loop like this and you're using it to work on a matrix, you have one loop that's going to be the row index, okay? And so that's going to loop over the rows. And you have another loop, which is going to be the column index, which is going to loop over the columns, okay? Okay. And so the i's, excellent, great. And so the i's here are going to loop over the rows and the j's are going to loop over the columns, okay? I want you to look at the kind of the output matrix here and look at kind of the patterns of where the ones are, right? And so you can see here we have ones. We have ones on the entire first row. Yeah. So the double vertical lines mean or. And so this is an example of a compound if statement. And I forgot this last year too, that I didn't go over compound if statements in the problem. Oh, your mic might not be broken, so the volume here is down low. I guess whoever used it before me turned the volume down. So it might just not have come through because they muted the volume here. And so what the or means is that it's going to check for conditionals, and then it enters into the if statement if any of them are true, okay? And so let me go ahead and switch to black here, okay? All right, and so I think we have I, and then a box, or J, and then a box, or J, and a box, or I, and another box, okay? Okay. And so I think I've given you that. Let me just double check real quick. Yeah, if I blah, blah, blah. Oh, I gave you this one. Okay. That's I is equal to 1. Okay. And then we have C blah, blah, is equal to 1. Okay. Okay. And so I've already kind of given you one of the conditions here, right? And so if you know that the loops are going on, one is the row index, one is the column index, when I is equal to 1, right? This corresponds to the first row in the matrix, right? Okay. Right, because whenever I is equal to 1, that's the first row. And so whenever we're in the first row, we're going to enter into this if statement right here, okay? And just kind of based on what I've given you here, you can see that what we're doing inside the if statement is we're changing the value of that entry to 1, okay? As we have C, I, comma, J is equal to 1. And so that lines up with what we see here on the matrix, right? And so for this entire first row, right? So whenever we're visiting this entire first row, we're going to set the matrix entry equal to 1, okay? And I is equal to 1 is the first row. Okay. Let's see where else do we see all ones, right? Another place that we see all ones is the last row, right? Okay. And so how do we express the last row, inside our loop using the I and J variables, right? And so I'll let you guys think of that. So I kind of took it almost all the way, but you know that the i's are going to be the row indices, right? And so you have i's equal to 1 is the first row, and so the last row is going to be, you're going to fill in the code right here for the last row. Okay. Yeah. So the if part, because it has all of these compound if statements, it's tough. Right? And then you can kind of guess too that the other place that we have the ones is the first column and the last column, right? But to specify the columns, we need the J variable, not the I, right? And so we're going to use one of these J's to be the first column, okay, and the second J to be the last column, okay. And so that's as far as I'll take it for you guys, because it's, you know, it's almost done already, but you know, hopefully that kind of explains the logic a little bit for that one. Yeah. Okay. Awesome. Yep. Okay, so it is almost 8:40, and so I haven't eaten anything today, so I am gonna have to cut it a bit short right now. But if you have any more questions on this, go ahead and shoot me an email. I don't know if I can get to it tonight because I need to walk to my car, and you know, probably when I get home I'm gonna knock out. But tomorrow morning I'll get to whatever email you sent. So thank you guys for coming today, and then I'll see you on Wednesday.